So do you have any questions? 11.1, anything?
Number 83.
Number 83. Okay. Yeah, okay. Yeah, that's a good one. Let's jump on it. Number 83 is a kind of a word problem, a navigation problem. It says a plane is flying with a bearing of 302 degrees. So right off the bat, that could be an issue. When they use the word bearing, and I remember this because we do some of these problems in a trig class actually. At the end of trig, you might do a little vectors, you might do some problems like this, and that word bearing, when they use the word bearing in navigation problems, then that's from due north. That starts at due north and is measured clockwise. So a bearing, anyway, so it's not the way we normally measure angles. We normally measure angles in what we call mathematical standard position. But anyway, that word bearing then implies from due north, we're going in an angle of 302 degrees. So let's see, this would be 270, so another 32 degrees past that, I guess. Right, you guys?
Yeah.
Okay. So the plane is headed off in that direction. I could draw a vector in that direction. If I knew the speed of the plane, it says its speed with respect to the air is 900 kilometers per hour. That means I should draw this vector 900 long. So yeah. So its magnitude is its speed, 900 kilometers per hour. Now that's what they said with respect to the air. That's kind of interesting. That's why these can be a little confusing. At that plane's altitude, there is a wind from the southwest at 100 kilometers per hour. So the wind is from the southwest. From the southwest. Okay, hang on. If that's north, south, east, and west. Right. So here's southwest. And when they mean southwest, they don't mean just general southwest. They mean exactly southwest, which is a 45-degree angle there between south and west. And, you know, if I drew this vector, that would be the wind blowing southwest. Hold on, that's wrong. But they said from the southwest, so it's from the southwest, so it's really blowing this way. Now, watch this. You could be tempted to draw that vector. Oh, by the way, that vector is only 100 kilometers per hour, so it's much shorter. But you might be tempted to do this. That's not good, though. That's from the southwest, but I'd rather, I mean, there's nothing really wrong with that, except I'd rather draw that vector. You can pick up and move vectors. They're all, as long as you don't, so I'm going to draw it here is what I'd like to actually do. And it's 100 kilometers per hour. And that's a 45-degree angle. So there it is. There's my wind. There's my airplane. Just get rid of some of this in here. You guys doing okay?
Yeah.
And then I think they want the speed and direction of the plane. Let's see what they say. What is the true direction of the plane and what is its speed with respect to the ground? So the concept is the instruments of the plane might say it's going in that direction, but due to the wind, it's actually not going in that direction. With respect to the ground, it's being blown off here a little bit. And so what I want is the engine on the plane says, you know, my speedometer, I don't know if planes have a speedometer, but it says I'm going 900, but reality, you know, against this wind or with this wind, I might be going a different speed. So what I really want is what the plane's doing added to what the wind is doing. I want what's called the resultant of this. I want the addition of these two vectors. And I've sort of taught you once that one way to add vectors is sort of visually like this. You grab that vector move him, put him here. I mean, that does make sense. The plane is trying to do this, the wind is going to affect it like this, and the result is what we call the resultant. The addition of those two vectors ends up being this result. So that's what I'm looking for. I'm looking for that, and I'm looking for that magnitude and that angle if I can find it. This is number 83 in 11.1, a good little word problem about an airplane and some wind, but it really is just adding two vectors. And you know, back in trig, you might do some fancy stuff here and work on using the law of sines or the law of cosines and try to work on this triangle here. I'll tell you what, I'd rather just add vectors using, the way I like to add vectors is add them component-wise, which means I'd like to have the x and y, I'd like these vectors to be in component form. Well, we've learned how to do that. I'm going to call this the plane vector, and it has a magnitude of 900. And I told you that to put them in component form, we're going to write an x component, which is 900 times the cosine of the angle. Now hold on a second. If I just do the cosine of 32, that's going to be a positive number. You know, when I say the cosine of the angle, I think I want the angle in standard position. I mean, maybe I can tell, you know, on this x and y axis, that's kind of a negative x direction there. If I use the 32, I won't get a negative x direction. I'd rather use the actual angle there. Let's see, so we decided that's 32, so this is 148. So here I am. That the black vector, the plane vector, is 900 cosine of 148 degrees, and his y component is 900 sine of 148 degrees. Good. The wind vector, which I'll call W, is the magnitude times the cosine and the sine of the angle. The wind vector is not very hard. He's in quadrant 1 there, so he's just 100 cosine 45 for the x component and 100 sine 45 for the y component. Good. Hopefully you understand that. I will decimalize these numbers. This is sort of a physics problem, word problem. I'll decimalize these numbers, I'll add them up, and I'll have my resultant. This is a nice problem. Yeah, this is pretty good. We had to learn about bearing, we had to learn, but ultimately it's just adding two vectors, and you were given magnitudes and angles, although you severely had to adjust that angle. And given magnitudes and angles, you needed components. Once I get these components, yeah, let's do this. So now it's a calculator exercise. I should be in degree mode, and maybe you can help me just decimalize these to maybe to 1 decimal place. I don't know. What is this?
That is negative 763.2.
And good, it came out negative like I was predicting. I mean, again, yeah, using that angle in quadrant 2, that should come out, yeah, good. And the y component?
476.9.
476.9, bless you. Good, and then the wind vector is 100, I think I know those numbers, 70.7. 70.7, okay, thank you, and 70.7, I think, because that's a 45-degree angle. All right, yeah, I want to add these vectors, and the resultant, I'm going to call it R, for the resultant will be, now, I mean, this is what I like. We like to add vectors component-wise. So it takes a little work to get it in component form, but then this is an easy problem. I add those numbers, that's negative
692.5.
692.5, comma
547.6.
5?
Yeah, 547.
Oh, 547.6, thank you. And that's my resultant vector. And I circle it, I think I'm cool, I think that's my answer. Actually, that's not what they wanted something else, or they want an additional little work here, because what they asked for was the speed of the plane now, its resulting speed and its resulting angle. So now I kind of got to go back. I mean, I have the vector, but how do I find his speed? That would be the magnitude of that vector. So I need the magnitude of that vector, 692.5 squared. Plus the 547.6 squared. Sorry. Yeah, and then added and then square rooted. Maybe you can give me a final answer here.
882.8.
Cool. 882.8 miles per hour, or kilometers per hour, I think it was. Yeah, that's my speed. That's the magnitude of the resultant vector. So that wind was slowing me down a little bit. You know, if that wind would have been, you know, if that wind would have been in a little different direction, maybe it would have been helping me out a little, right? And maybe I mean, it can kind of help me or hurt me, you know, or so you kind of don't know. Sometimes the picture is misleading, but that wind was slowing me down a little bit. Yeah, not that much. And it threw me off course a little bit. I wonder how, let's see, I'm looking for this new direction angle, kind of, for that blue resultant vector. How do you find a direction angle? Tangent, inverse of the y over the x, the y over the x. That is theta. Now, but we may need to adjust that. So a calculator will tell me that in degree mode. Maybe, what do you guys think?
It's negative 38.3.
Thank you. So yeah, it's a negative number, which is going to, according to, we had these big discussion the other day, it's a negative number, and tangent inverse of a negative number will be an angle in quadrant 4. We're either in quadrant 1 or 4 due to the restrictions of tangent inverse. So say it one more time, negative 38.3 degrees. Okay, thank you. But now wait a minute, we look at the picture and that's not negative 38.3 degrees. I mean, the calculator just told me negative 38.3 degrees. You know, what I could do is say, okay, that's my related angle or reference angle. So I could go over here and say that's 38.3 degrees, which basically means subtract it from 180 or add 180 to this, same thing, and that'll be the answer. So we'll add 180 to this. And what is the answer now?
141.7.
141.7 degrees. Now, hold on. I'm going to circle that and call that my answer. But that's the name of the angle measured in standard position. Because this is an airplane problem, they actually might want bearing. Remember when this problem started, they gave me a bearing, which is measured from due north. Well, then maybe they don't want this. You see what I'm saying? In a vector problem, in a math problem, we put the answer in standard position, measured from the x-axis that way, and I think we got the right answer. But if oh boy, all right, so, so here's our result, and that's 141.7, that's 38.3, let's see what I could do. What could I do? If I wanted to use the word bearing, I would start here and go 270 plus 38.3 actually. So maybe my answer should be a bearing of 270 plus 308.3. Another way to talk with these bearing problems is I could say, I just added this to 270 this time, just because of the language of bearing. I could say it's 38.3 degrees north of west. That's another way to talk. 38.3 degrees north of west. I could say that. It's kind of another way to speak in bearing language. That was a fun problem, though. I like it. You know, again, part of the language and the drawing and everything is probably the skills you needed. What really wasn't, what made it kind of easy was the concept of, to add these vectors, you just do the, you turn them into components and add them. But there's kind of a lot there. I mean, that was a good question, you know, again, because of the bearing and all that. I was going to call your attention to like 77 or 78, which is, and then these, there might be something like this shows up again in 11.2, but let's look at 78. And because we did this one, I don't really feel like I have to probably complete 78. But let's just take a look at it, and you can try 77 or 78. What it says is these. I got these three forces. So I'm going to call it force 1, force 2, and force 3. And they gave me a magnitude for each force. They said 3 forces with magnitudes of 400, 280, and 350. All right, hold on. So this guy has a magnitude of 400. Forgot already. 280 and 350, 280 and 350 newtons of force, and they're acting on a point. These 3 forces are acting on an object. They're kind of acting on a point at these angles, respectively. So the angles are negative 30, 45, and 135. Now I could just jot those down like little notes, negative 30, 45, and 135, but what do you think I want to do with those angles?
Component.
I want the cosine and the sine of those angles to put this into, so I'm going to go ahead and write this. Cosine negative 30, comma, 400 sine negative 30, and make a vector out of that. Right, there's force 1 with its magnitude and direction angle. And force 2 would be cosine, I think it was 45.
Yeah.
And 280 sine 45. So without even drawing a picture, I got an angle. You put them into components. And the last one was 135. Cosine 135. Sine 135. By the way, they're not using the word bearing here. These are in standard position. I just used those numbers that were given. And so these 3 forces act on this object. Find the direction and magnitude of the resultant. That's just like what we just did, right, you guys?
Yeah.
I mean, decimalize. I don't think I'm going to finish this, but I'm just going to describe how to finish this. Decimalize those, add them up, and then you're still not finished. To get the direction and magnitude, you need to finish this, right? To do this work. Those are good problems. Those are classic problems. I like to put that on a test or a quiz. Sometimes it sneaks up and gets students. I don't know. They forget how the prescriptive method to do this. I don't know. It's not, once you know the method, it's not too hard. By the way, I think, these are physics types problems, and the truth is, in physics class, I think this is sort of the technique. They give you a magnitude and an angle, and you put it into components and add them like this. Okay, cool. So I won't finish that. Oh, you know what I was thinking of doing, though, was just drawing this for you. I want to show you something here. I don't know. It's just funny. To me, this is a little funny. But they say these 3 forces act on this point. And so we'll make the point to be the origin. and so they're acting on this point. And so, like, you might, don't do this for a second. I'm going to do something wrong here, okay? So, like, if it's acting on the point at a negative 30-degree angle, I mean, here's negative 30 degrees. I might think it's acting on the point like that. And then 45 degrees is here, it's acting on the point. And then 135 is over here, that's acting on the point. I mean, when they're acting on a point, I sort of feel tempted to do this, but this is a mess. Do not do this. Do not do this. What I'm doing is I'm drawing the vectors like pushing on this point. Okay, it's better to draw the vectors pulling from the point. I mean, this is totally not accurate. I mean, if this negative 30 degree angle, this is wrong. What I should do though is just simply have my arrow go the other way. A vector that's acting at a negative 30 degree angle is sort of pulling on that point. It's acting on that point. Like I said, it's acting on that point. That phrase tempts me to draw the arrow that way, but let's pull on the point. And then you're doing it right. Anyway, and that one should be 400 long. This one is going at a 45 degree angle. It's only 280 long. I don't know how good a job I'm doing here. Not too bad. And then this one's 135 degree angle. Watch this. 135 degree angle. It's 350 long. Huh. Yeah. It's supposed to be longer than him, but a little shorter than him. Anyway, those are my three forces. Now again, to get the result, you're going to do the math. But you could watch this pictorially, just for an estimate here. Pictorially, I'm adding these three forces. So I'm going to grab him, put him here, keep him the same distance and same length. The resultant of those two then is this. Now I'm adding him with him. So I'm going to take this one and put him over here. Try to keep him parallel, try to keep him the right length. And now I'm adding the blue one and that black one there, and then the final result is going to be this one. So I don't know. You could try to go do this problem. At the end of, over the weekend maybe. Hopefully get some kind of answer there. I don't know what that is, roughly 50 degrees maybe, roughly. Anyway, using a rough picture to get the answers might be a good guess if I was fairly accurate. Cool. Any other requests? We started with one request, and I elaborate, and it takes a while. Any other requests from 11.1 homework? All through this chapter 11, we're doing some neat things with vectors, and we got more to learn, and we're in space, and we're going to think about planes and spheres like we started to in 11.2. And so guess what? I've told you this maybe before. We hardly do any calculus. Hardly do any calculus, but in 11.1, there are these problems. There are these problems. I'm going to do number 70. Number 70 in 11.1, I think does a teeny bit of calculus. It says, the directions are a little funny, it says find a unit vector that is part A parallel to and part B perpendicular to the graph of this function at this point. So I have this function, f of x equals x cubed. And they say I'm at this point, -2, -8. And I think I will draw a picture of this. That was part of their directions also, was to draw a picture of this. This is fairly easy to draw. It's a cubic function. It kind of comes up here like this. That's kind of what that is, what a cubic function looks like. And I'm at this point, -2, -8, which, see, I'm not, well, anyway, -2, -8. So I'm a little rough here with this, but that's okay. I'm at this point, -2, -8. And what do they want? Oh, they want a little unit vector that's parallel to and another one perpendicular to this graph. Now, wait a minute. I'm going to act like an idiot here for a second. This is a curvy graph. How do how can you be parallel to a curvy graph? And you would say, these calculus students, you would say, at that point, what they want, parallel to the graph at that point means I should be parallel to the slope or to the tangent line, right? I should be right. How can I be parallel to a curve? I can be parallel to the tangent line to that curve, right? So it's all about the tangent line. That's what they mean. They want me to be parallel to and perpendicular to some tangent line. Okay, well, I know how to be parallel to a tangent line. I wish I knew the slope of the tangent line. And as soon as I say that phrase, slope of the tangent line, this is calculus, but but we haven't done any calculus this semester. The slope of the tangent line is the derivative. Thank you, thank you. I need a derivative. That's all. I need a derivative. I need the slope of the tangent line. Right. I need the derivative. The derivative is easy. It is 3x squared. At this point, when x is -2, very specifically, f prime of -2, the slope, this is the slope of the tangent line in general. At this point, the slope of the tangent line at this point is 12, huh? 12. That's the slope at this point. Now this is cool. I mean, you know, I've been talking about vectors, and I never really used the word slope because we don't really say that a vector has a slope. We talk about its components. It's got a, you know, in a way, you know, the components of a vector describe how it changes. This is how much this is the change in x, and this is the change in y. This is how much it runs and how much it rises in a way. I mean, we don't write it as a ratio and call it a slope. We write it as an x and a y component. But it is sort of, I mean, you can interpret that as a slope or reinterpret it as a slope. So if this slope is 12 or 12 over 1, how could we write a vector out of that? I mean, I want a vector that has that slope. The key is,
well, does that mean the slope's 90-degree angle?
well, no, the slope, well, it's steep, it's 12. The slope is 12, 12 over 1. The 12 is the slope, the 12 is the change in y over the change in x. That's what a slope is. A rise over a run, or change in y over a change in x. So how do I write a vector like that does that? (12(1)? Maybe I write 12(1). Maybe not. I mean, wait a minute. The y is the 12.
Oh, I got you.
And the x is the 1.
It's like a tangent, right? Inverse.
Well, I just want to write the vector components that go up 12 and over 1. A slope is a rise over run. It goes up 12 over 1. That's the slope at this point. It's this ratio, 12 to 1 ratio. Can I write a vector that does that? Well, yeah, the x should be 1, and the y should be 12. Because it'll go over 1 and up 12, or that's what this says, up 12 and over 1. I mean, right, we got it. We got it. That's a parallel vector. Maybe I didn't. Maybe you knew that. To be a parallel vector, it should have the same slope. It should have the same slope. So we made a parallel vector. We made a vector that has that slope. You know what we didn't do, though? The question asked for a unit vector. They wanted what they wanted was a parallel unit vector. And I ignored that for a second, and that's my advice to you. When you have a problem that asks for a unit vector, listen, if you get hung up on that word unit vector, I mean, you know what a unit vector is. Its length should be 1. But if you get hung up on trying to make it length 1, oh my God, you'll never get anywhere. So forget that for a minute. Find the damn vector you need. Can't you always make it a unit vector? Can't you always shorten it up by
Dividing by its magnitude.
dividing by its magnitude? Thank you. So the answer is, this is the answer, divided by his magnitude. What's his magnitude?
12.
Well, no, his magnitude. You know his magnitude.
Oh, it's 145. Square root of 145.
Good, good, thank you. The square root of 145, thank you. Which is almost 12. I mean, it's 12 point something, but it's the hypotenuse of, yeah. Cool, that's the answer. That's the answer. If I drew a little vector that went, whatever, over 1 over the square root of 45, 145, and then up 12 over the square root of 45. I mean, that would be a little vector that's 1 unit long. It's a parallel vector. It's parallel at that point. Hey, is that the only parallel vector?
There's probably like multiple in that same direction.
Well, oh, yeah, that's true, of various lengths. Yeah, that's true. But if they have to be length 1, then he's the only one. Or is there another parallel vector? What about going the other way? That's also parallel. That's also parallel. And to go the other way, how do you make this guy go the other way?
Multiplied by its reciprocal.
Yeah, no. To make him go, and the opposite vector would be the negation of this vector. It would be, and I'm not thinking about slopes. See, you might be thinking about slopes. See, now I'm just thinking about vectors. If this is a vector v, what's negative v? It just points in the opposite direction. Yeah. Exactly opposite direction, 180 degrees, exactly opposite direction. So there's 2 answers. That's one parallel vector, and the opposite of him is the other parallel vector. The way I write that would be maybe like that. The negative version of him and the positive version of him is my 2 answers for a parallel unit vector. Whew. It's not too hard, but it took some digging. I had to dig that out of you guys. Part B wants a perpendicular unit vector. Perpendicular unit vector. You know, I do want to make, I guess I want to make the connection back to slopes again. So this does take me back to ancient algebra. Not ancient, but I mean, you know, do you remember about lines and slopes? I mean, when a parallel lines have the same slope. So that was the first concept there, was we needed something with a slope of 12. But now if I want it to be perpendicular, then it's the reciprocal, hang on, it's the negative reciprocal actually. That's the old algebra. So now I need a vector with a negative 1/12 slope. Now listen, can you help me get a vector with a negative 1/12 slope? And by the way, I guess if I call this V, I'll call this one W, just to avoid the same name. Can you write me a vector with a negative 1/12 slope? Again, we don't talk about slope with vectors, but we do have a change in x and a change in y. What's my change in x? No, because slope, the ratio is the change in y over the change in x. So who's the change in x? The 12. Who's the change in y? The negative 1. Are you with me?
Yeah.
I mean, this is x and y, but with a slope, that's not x over y. I mean, so you got to, right, the denominator's x, the numerator's y, with a slope, right. So cool, we got it. Oh, you want to make him a unit vector? Now you can make him a unit vector, divided by his magnitude, which is the same magnitude, Okay, cool. Now it's a unit vector. Now let's just check this little guy out. He goes over whatever that number is, 12 divided by the square root of 145, 0.999 something. He goes over that much, and then he goes down -1 over that, some teeny little bit. He's a little unit vector. He goes over and down a teeny bit. Here he is. Look at him. Does he look perpendicular? I think he looks perpendicular, perpendicular to the tangent line, perpendicular to the curve. But is there another one that's perpendicular?
Yeah.
Yeah, his opposite. His opposite. So his opposite, what I'll do is I'll put a plus and minus in front of this. And there we go. There's technically kind of two answers. Maybe. All right, that's good, you guys. I like those problems. I think that's a good test question. There's some good, there's a few there. There's a little group of those you can practice in the book. I assigned those. You know, on a test, let me just say this, on a test I like to make the derivative a little tougher. I mean, a derivative is pretty easy. It's the only time I get to do any calculus in this chapter. We'll get to do plenty of derivatives, we'll get to do integrals, we'll get to do plenty of calculus in the rest of this course. But chapter 11, we don't get to do much calculus except for this question. So I don't know, if I was making up one, I might make up a function that's a little more interesting. I might make up a function like this. And if you had to do the derivative, what would you do?
Is it a product rule?
A product rule, yeah. So I'm testing you, some of your old knowledge a little bit. Right. Let's just do it for fun, even though I'm not going to finish this problem. The derivative of the first. 2x times e to the x plus write down the first and take the derivative of e to the x.
Same thing.
E to the x. So right. And then I have to give you a point, and then you can find a slope. I mean, that's the key. The key is you find the derivative leads you to a slope, and then the slope leads you to a vector. Right. I don't know. Well, check this one out. What if I did this one to you? 5 cosine 4x. Can you do that derivative?
Chain rule?
Yeah, thank you. This is not a product rule, but there will be a little chain rule. What he's saying is, when I get down to it, I think I'm going to spit out a 4. That's the chain rule is going to spit out a 4 at the end. But let's start at the beginning. We would have what? The derivative of cosine?
Positive sign. Or is it negative sign or positive? I forgot.
All right, hang on. I mean, I remember these two things. The derivative of sine is cosine. Therefore, the derivative of the cosine is negative sine. I mean,
yeah, I always get the integral and the derivative.
right, so then when you integrate, you got to remember those derivative rules backwards, so I just remember the derivative rules. Darn good. The derivative of sine is cosine. The derivative of cosine is negative sine, so it would be -5 sine 4x, and then you said the chain rule says you do the derivative inside there, and that tacks on, multiplies on at the end, and that would be a 4. It's multiplied 4 out on the end, but it's actually, you could call that -20 sine 4x, right? Yeah. Anyway, all of a sudden I just warped into practicing derivatives here just for a second, but I'm just saying, I like these problems, and if I'm making up a test, I like to notch it up just a little with a little more interesting function. All right, maybe I'll flip the page into 11.2 here. We talked about spheres a little bit and just points in space, just trying to get used to three-dimensional space, plotting some points. kind of like this question. Yeah, I think I'm going to just jump up here and do this question. So I'm in 11.2, and I'm going to try this problem 52. And I think I assigned 51, but I'm going to do 52. And it's just, it's pretty easy, but they get pretty wordy with this. So here's what they do. In 52, they give me an initial point and a terminal point. Let me write that down. They give me an initial point and a terminal point. I know what that means. That's my vector starts and stops. If I 2, -1, -2, 2, -1, -2, and -4, 3, 7. -4, 3, 7. But now if I read these directions, let's see what they want. They say, sketch the directed line segment. By the way, a directed line segment is sort of a line segment with an arrow on one end showing direction. That could be what a vector is, a directed line segment, right? But they say sketch the directed line segment, and then part B, find the component form of the vector, and then part C, write the vector using standard unit vector notation. Okay, and then sketch the vector with its initial point at the origin. Oh, okay. You know what? I should have read that a little better. I kind of thought they had a different idea. But that's okay. I want to do this anyway, maybe. But this is kind of easy. Let's see. But I am in space, which means this may not look good, right? We kind of learned that this might not look good. But we'll try it. 2, I want to find these points. 2, -1, -2. 2, that's out here on the x. -1 is going to move me in the y direction negative. This is x, this is y, this is z. There's the negative y-axis. Here's the negative x-axis. Here's the negative z-axis. Okay, hang on. What did I do? 2 for the x, -1 for the y, and then I need to go down 2 for the z. So I came out 2, over 1, and down 2. And that's my initial point. I don't really want to see these other points. My terminal point. -4 on the x, -4 on the x, 3 on the y. I go over from where I was at, over 3, and then 7, 1, up. I try to go parallel to the axis. That's the key. Kind of when I moved over, I went parallel to the y-axis. And I went 7 up. So anyway, there's that point. And the directed line segment would be from the initial to there. It's going to look like crap, but it's just, yeah, that's it. I guess, something like that. It's worse. When I try to fix it, it looks worse. Okay. All right. A directed line segment. From that point to that point. Okay. All right. Then what did they say? Find the component form of the vector. Do you know how to find the component form of the vector?
You do terminal minus initial.
Terminal minus initial. We said that the first day. That was kind of just a little catchphrase. But that is, again, it's kind of like this. It's kind of like, what's the change in x? What's the change in y? What's the change in z? I mean, that is kind of the components of a vector. That's what a vector kind of is. So I can subtract to find that change. Sometimes I can just see that change. I almost screwed that up though. Hang on. So I will subtract. -4 minus 2 is -6. 3 minus a -1, I think, is 4. 7 minus a -2 is 9. So I guess that's what this vector has to do. To get from here to here, it has to go back 6, over 4, and up 9. And maybe I can sort of see that after the fact. Or during the fact there. Cool. There it is. find the component form of the vector, write the vector using standard unit vector notation. Do you even know what that means?
We just use the IJK form.
Yes, that's what that means. Using the so that's, to me, that's kind of pointless, but it is good for you to understand that that's the same. This is the same as this. Negative 6i plus 4j. That's how you do it. You don't put commas. When you're doing this, you're adding these little unit vector things like that. Okay? Let's see what else they say. And then sketch the vector. Oh, because then if somebody just gave you this vector to sketch, you would go start at the origin. Again, this is sort of, I said, kind of these thoughts. So I would start at the origin and I would draw this vector. This is kind of messy, but I would go back 6 over 4 and up 9. And draw that vector. Oh, that's a mess. Probably looks real good on the video. Anyway, they should be parallel. I mean, it's parallel. It's all pointing in the same direction. Starting here or starting at the origin, both of these are going back 6 over 4 and up 9. That's what they're doing. Wherever you started at. I don't know. I kind of thought this might be interesting, but I kind of thought that question was headed in a little bit different direction. So I'm going to take you in just a little bit different direction. The picture is not that interesting to me. You know what I was thinking? I was thinking these are 2 points, and I want to find the distance between 2 points. I want to find the distance between 2 points. And I didn't mention this the other day, but when we got into 11.2 and we're in space, the book mentions the distance formula in 3D. Now, that means maybe you should recall the distance formula in 2D. The distance formula was always the square root of the x2 minus the x1, the y plus the y2, hang on. The x2 minus the x1 squared plus the y2 minus the y1 squared. That was the old distance formula back in XY world. But now in 3D, what do? Z2 minus Z1 squared. I just add, that's it. So I want to find that distance using the distance formula. Okay, well, here I go. Let's see, what do? Subtract the x's and square it. I think that's negative 6 squared, right? Or however you subtract. Negative 6 squared plus 4 squared, I think. And then subtract the z's. That's a 9, right? That's a 9 squared. And we get this distance. 36 plus 16 plus 81.
11.53.
Well, you know me. I don't like that answer. 36 plus.
That's 133.
All right, the square root of 133, thank you, which is approximately 11 point whatever you said. Okay. All right, anyway. All right, give me 2 points in space. Can you do a distance formula in space? Sure. Here's the connection I'd like you to make is, can you find this distance using vectors? And so we had this starting point, and we had this ending point, and I had a vector drawn up here. Can I find that distance using a vector? Just use some knowledge. What are you thinking? Can I find the distance using vectors? I mean, what do you think I should do? What's the word? I mean, just... If I have 2 points, I want to find the distance. Let's forget the damn distance formula a second. I don't want to do I want to find that distance, but I want to use a vector. So what would you do?
Midpoint?
No, I want the distance. But I want to use a vector. Okay, I got 2 points. So I think I should do terminal minus initial. That'll create a vector. But now how do I get this distance? Okay, that distance is the length of the vector, you guys.
So something about a unit vector?
Well, no, it's just the length of the vector. What's the length of the vector? What's the word? That's the,
Scalar?
no. Sorry.
Is it the magnitude?
The magnitude.
Yeah.
Yeah, the length of the vector is the magnitude. So now, what am I saying? I got 2 points. Can you do terminal minus initial, create a vector, and then find the magnitude of the vector? Now watch what happens when we do that. Okay, that's what we did. Well, watch. We got 2 points. We do terminal minus initial, create a vector. Okay, bam, we did that. Now I want the magnitude of that vector. And if I do the magnitude of that vector, it is, of course, the square root of 36 plus 16 plus 81, right, you guys?
Yeah.
So, I don't know, what's my point? My point is we practically just did that. I mean, the distance formula makes me subtract points. Creating a vector makes me subtract points. The distance formula makes me square them and add them up and take the square root. Doing the magnitude of a vector makes me square them, add them up, and do the square root. I don't know.
So it's like an alternative way of doing it?
I don't know. It's the same. It's almost the same math, but it was just stated as a distance formula and the magnitude of a vector. I mean, it seems like different things, but like it might ought to be 2 different formulas or something. But it's the same math. You subtract the x's, subtract the y's, subtract the z's, and do the magnitude of the vector. This distance formula is what we did here. Yeah. That was my point. All right, anyway. There might be a problem that does make you think or talk like that. Actually, maybe I'll just stop with this homework. We got 15 minutes. I might just talk a little more here, and I might not get. Let's see how far we get here. I'm just going to push ahead a little before the weekend, and then let's get out of here. So we've been working with vectors, 2D, 3D, magnitudes, unit vectors, angles, direction angles. We can add vectors, we can multiply vectors by scalars. Okay, but here's something we haven't done. We haven't multiplied 2 vectors. And that's what comes here in 11.3. In 11.3, it's called the dot product. And it's the multiplication of 2 vectors. We call it U dot V. But, I mean, and I don't, not to confuse you, but there are 2 ways to multiply vectors. So in 11.3, we'll discuss the dot product. I'll teach you about that in just a minute. But I just want to tell you that there's another multiplication of vectors up in 11.4. We call it the cross product. It's a different type of multiplication, you know? When you're dealing with numbers, you've got multiplication. You don't have 2 types of, anyway, we got 2, with vectors, we have 2 types of multiplication. So the notation here, we call it a cross product, or we use this notation. So it's a different type of multiplication. Let's discuss one at a time. Let's not confuse the issue. So if I have a vector u, and it's u1, sorry. And so now if I talk abstractly here, u1, comma, u2, comma, u3, just talking in general. And then I have the vector v, which is, you know, v1, comma, v2, comma, v3. Gotta watch your u's and v's, they almost look the same. Then the dot product is this. It's easy to do, it's very easy to do. You multiply the x components, you multiply the y components, you multiply the z components, and you add them together. Let's do it. I mean, it's u1 times v1 It's U2 times V2, and it's U3 times V3, and they are all added together. Now notice, I mean, I'm multiplying numbers, I'm multiplying numbers, I'm multiplying numbers, and I'm adding it up. Guess what? I get a number. And so the answer to this is not a vector. When you multiply these two vectors, I mean, maybe you should know, you should look at this and kind of know, this is not a vector. Not a vector, and when it's not a vector, it's a number. The word we use for that is scalar. We kind of barely have used that word, but it's a scalar. That's not a vector. It's a scalar quantity, it's not a vector quantity. And that's kind of an important point to drive home. I have seen students, they'll do the dot product and they'll screw it up. You know what they'll do? They'll put little commas in here and vector symbols around it, and that's bad. That's very bad. I mean, it's not a vector. There's no commas. You add these things up and you just get a number. What does that number mean? Maybe we'll get there. It's a number or a scalar. In fact, sometimes then we call the dot product, sometimes we call it the scalar product. The scalar product. So you can kind of just do dot products. They're useful for a few things. They're useful for what's called projections. Sometimes I skip over that. That's a little bit more of a physics topic. They're useful here. If you have a vector u and a vector v, I'm just drawing kind of abstract vectors. You know, when I draw these vectors, you know, they're on a flat board. You might think they're 2D vectors, but I'm trying to, in general, pretend they could be 3D or 2D. So they're just two vectors with their tails together. You know, I mean, they're, you know, here's two vectors with their tails together. You know, and they're just out here in space, somewhere in space. And then they might have an angle in between them, or they do. There's an angle between the two vectors. And that's not, you know, that's not our old standard position angle of a single vector. This is called the angle between two vectors. And the dot product can help me find that angle. I'm not going to prove this formula to you, but the formula is this. This is a good one. You need this one for tests and stuff. The cosine of theta, the cosine of that angle, is the dot product of the two vectors divided by the magnitude of u times the magnitude of v. That's a cool little formula that uses the dot product in this formula, and it can help me find the angle between two vectors. Let's just try one before. Find the angle between the vectors. That's how I would say this, I guess. A little sloppy there, but find the angle between the vectors. U is 5, -7, 3, and V is 4, 2, -5. So these are a couple vectors in space. I don't really want to draw them, but I've got two vectors in 3 dimensions. I can put their tails together. Well, you know, if I draw them from the origin, their tails are together, and I want the angle between the two vectors. And I'm going to do this formula, I guess. Let's check it out. Here we go. I need cosine of theta is, okay, the dot product. Now this is easy, you guys. We haven't done one yet, but I told you how to do it. Multiply the x's, multiply the y's, multiply the z's, and add them up. That would be 20. I'll just write it down. 20 plus -14 plus -15. Okay? Which, what is that, a -9? That's a -9. Over the magnitude of each of the vectors. So now I need the magnitude of u. The magnitude of u is probably the square root of something. The magnitude of u is, oh boy, 25, 49, and 9.
83.
83. Square root of 83. That's the magnitude of u. 25, 49, and 9 added together, square rooted. I like to do them in my head, but you gotta be careful. The magnitude of v. This is multiplied by the magnitude of v. Probably also 16 plus 4 plus 25. 16 plus 4 plus 25. The square root of 45. Okay, well, I added up my numerator, my dot product, and it turned out to be this number. So the dot product was the -9. These two magnitudes are just a little nasty here. But how do I go about finding the angle now?
Take the inverse.
Yes, the inverse cosine. So the angle is the cos inverse of this. So we have to be able to type this in your calculator. You want to be in degree mode, and and you know, you gotta keep this division. Maybe you need parentheses on all that. The truth is, you could join those square roots together. You could call it the square root of
3735.
Okay. You multiply those numbers. 83 times 45. Thank you. 3735, right? I mean, everyone do it. You get your calculator. But anyway, yeah, here we go. What does my calculator say about the cos inverse of that number?
Gotta do that radian, right?
Well, I like degrees. No, I mean, and they're gonna, either way, it's a nasty, it ain't, right, it ain't a famous angle, it ain't 60 degrees, or so it's a nasty angle, and I just assume talking degrees here for a little while,
Then 98.5.
98.5 degrees, okay? Anybody agree with that?
Yeah.
Okay, good. Good, that's the answer to that. Find the angle between the vectors, 98.5 degrees. Okay. I'm going to say a few more things, and then we're going to quit today. I'm not going to get to this cross product. We'll get to that next week, maybe Monday. It's pretty cool and pretty useful and different, quite different. So here's something. So what I had was, like I said, two vectors in space. Now look at me a second. So two vectors in space. Now, they could be anywhere, you know, but anyway, but you can move vectors as long as you don't change their length, don't change their direction. Anyway, and you can put their tails together. And when you put their tails together, then, you know, there is an angle in between them. But what's interesting, when you put their tails together, they sort of form a plane. And they form a plane. They're in a plane. And that's the exciting conclusion to this chapter is all about kind of these vectors. These vectors form a plane, and there's another vector pointing out. Anyway, we're going to build toward that. But I'm just saying, a couple vectors in space, when you put their tails together, they form a plane, and then in that plane you could draw this angle. You know, and maybe you would argue that there's two angles. But one of them is, maybe there's 360 degrees total. So what we always do is we say the lesser one. So we don't say, I mean, so if one of them's 100, I guess the other's 260, but we don't ever say 260, we say 100. So that's what we mean. So we don't have an argument whether there's two angles. Okay, now hold on. So the one we say will always be less than 180. Right. I mean, at worst, those two guys could be like this. And if they're like this, the angle between them is 180. And if it drops down a little bit, oh, now the angle's more than 180. Well, no, it's not. It's 179. You know, it's the other one. It's the smaller angle. So the angles, when you do this, the angle is always between 0 and 180. Now listen, when you use cos inverse on your calculator, its restricted range is between 0 and 180. So you don't have to ever adjust this. This is always your answer. You know, we were having that adjustment problem with tan inverse at times, but not here. Whatever they have, that's the answer. So, you know, I don't know what these guys really look like, but oops. But their angle is 98.5. That's a fairly accurate picture. You know, I knew it was going to be, so listen, so I'm saying when you find the angle between two vectors, it's always between 0 and 180. And you're using cos inverse to get you there, right? Okay, listen. So here's what happens. When you do this, remember I said